first reaction that is given. So you can read from the PDF first reaction. So there are several reactions, those occurs very fast, like and those reactions, first reactions. So how fast? The first thing I should say, how fast these reactions are. So normally, if you study standard reactions, you will see rate constant will be of the order of, if you do the reaction, 10 to the power minus 3 to 10 to the power minus 5, 6. I am writing with the minus 3 to minus 5. Let it be minus 6. So in that order, I'm not writing the unit because depending on the order of the reaction, unit will vary. So the value will be of the order 10 to the minus 3 to 10 to the minus 5. Okay. So now few reactions, these will be very fast. In that case, rate constant may go of the order of 10 to the power 10, 10 to the power 12. That means if it is minus 3 to minus 5 and it is 10 to the power plus 10 to plus 12. Okay, so the time scale, time required to complete these reactions, you can see it will be in the order of nanosecond to picosecond. So nanosecond means it is order of 10 to the power minus 9 second, and picosecond means 10 to the power minus 12 second. Okay, so these are the fast reactions. So those fast reactions, like if you shine with laser, laser will have high beam of photon, high like number of photons will be very large in laser. So those laser technique, if we use, then for those reactions it will be completed within the order of 10 to the minus 9 to 10 to the minus 12, and rate constant will be very high, order of 10 to the 10 to 10 to the 12. So these reactions will be very difficult to monitor in normal standard procedure. So there are several techniques through which you can monitor those reactions. Okay, so several techniques are there. Like in your syllabus, flash photolysis one is given. So one is flash photolysis. So like that you can, so these are the techniques by which you can study the first reaction. So one is flash photolysis, so relaxation method, and then you can study by flow techniques. So different techniques, these are like advanced technique which are used to study the first reaction, flow technique, and other methods are there, and I will discuss just in short flash photolysis because that is given. You can, no need of like there will be huge background behind flash photolysis or other method or rate equation, but qualitatively you can read the technique flash photolysis. Okay, one schematic diagram is there, you can see from the PDF. And relaxation method, there is a rate equation formation in that PDF also, but I will suggest no need of like it is not required, because flash photolysis that is only given, or question most probably will be asked from flash photolysis. So relaxation method, flow techniques, and other several techniques are there. At least you can read what will be the order of the or time required to complete the reaction or rate constant of these techniques. You can measure the kinetics. Okay, so in flash photolysis, what we will do in flash photolysis, and this techniques are also important to study the reaction mechanism. Sometime you know that in the reaction, when it is going on, different intermediate will form, because reaction mechanism means we have to study the how reaction is going on. So reaction mechanism we have to know, then we should know what are the intermediate species are formed. Okay, so this intermediate species, it will be having very short lifetime, because this intermediate you cannot separate or isolate from the reaction mixture. This intermediate can be free radical, this intermediate can be some free radical, some ion. Okay, so these species you can, it will have very short lifetime. Okay, so you cannot separate them from the reaction mixture. So what we will do in the flash photolysis technique, we can study the kinetics as well as we can identify what type of intermediate or species are formed during the course of the reaction. Okay, so that's why these techniques are very important, and two scientists, I think one is Norrish and another one you have forgotten his name. So 1967, you can see the period, they got the Nobel Prize for the discovery. Okay, Nobel Prize for the discovery of this flash photolysis technique, or very fast reaction, how you can monitor. Okay, so several techniques are there, out of which flash photolysis you can study. Okay, so Nobel Prize. Now, what we will do in flash photolysis? We will have a, and there will be two source of light. Okay, so light, or I can say electromagnetic radiation. So one will be pump, another will be probe. Okay, so these are known as pump probe techniques. So in that case, pump will have a laser source, and these lasers, it will have a laser source, and you will have your compound or reaction mixture, and there we will shine the laser light. Okay, from the pump, that source is known as pump. So from there we will have a burst of photon through laser. Okay, and this laser will have very short lifetime, very uh, high energy radiation with very short lifetime. So that lifetime can be varied from microsecond to picosecond. Okay, now what will happen whenever you will, pico is -12. So when you will shine high energy radiation, molecule may generate some free radical, ion, or some intermediate species. Okay, so then immediately we will switch off the pump, and like molecule, let's say your molecule M goes to the M star state. So M star is the reactive state. Okay, so this reactive state, what you have formed, that you can monitor by probe pulse. So this will be another pulse. So pump will be initially laser light. It will have very short lifetime. So nanosecond, picosecond, or maybe microsecond, it may vary. And then immediately we will switch off the pump, and then we will switch on the probe pulse. So probe will be another radio frequency, or any other frequency of light will shine, depending on what type of species you are willing to study. According to that, we will shine the light with different, depending on the nature of the intermediate, we will vary the time scale of the probe, what type of probe or what type of species are formed. According to that, probe pulse will be varied, and we can study the interaction with the probe pulse and intermediate species. Okay, and according to the lifetime of this intermediate species, it will give you the product. Okay, so that M molecule will go to the excited state, and then it may react with something else, or it may break down to give you the product. Okay, so when it is giving you product, how fast it is giving, according to that we will choose our pulse nature of the probe. What type of probe we have to choose depending on the frequency range, depending on the time scale of the probe, we can vary. Okay, so we will monitor with respect to time. Okay, this M star will be converted into product, so we will monitor their lifetime, or how fast it is decaying. M star is converted into product. We will study by varying the time scale, by changing the nature of the probe. Okay, so you know frequency, if you vary, its energy will change of that radiomagnetic electromagnetic radiation. So by choosing proper probe, we can study the nature of M star. Okay, so this is a like big technique, like it will have huge variations. What type of species you want to study, according to that you have to choose the probe. Okay, so in short, you can read the PDF, what is flash photolysis. Okay, so like it cannot be explained in like in few words, but you can study the general concept, how first reactions you can monitor through flash photolysis. So one will be pump, one will be probe. So first, using pump will shine high energy photon with very short lifetime. That will be mainly a laser source, and after that we will switch off the laser, and what type of intermediate has formed, that we can study by switching on another electromagnetic radiation, that is probe, and that probe we can choose according to the intermediate. And over the period of time, that M star will be converted into product, so we can see the nature of the, we can see the interaction of the light, that is given, light in the sense electromagnetic wave, that is coming from probe and M star. They will interact among themselves, and you will get some signal. Okay, so that we can record through spectroscopy. So that is known as transition state spectroscopy, because this M star is an intermediate or transition state. Okay, so this short note you can read. Then kinetics topic, I can say I have completed. So this small topic, it was left out, so I thought I should complete today. Any question from this one? Okay, so then I can move on catalysis part. Okay, so kinetics, you can where is that eraser? So kinetics you should study. There are several topics under kinetics. First order, order of the reactions, rate of the reactions, and then if it is first order, starting from zero order, first order to nth order, and how rate equation will change, what will be the rate constant and their unit according to the order of the reaction. And then comes complex reaction, parallel reaction, consecutive reaction, and then chain reaction. Chain reaction, HBr formation, that one you have to study. and you should study this topic, flash photolysis. Just concept you should develop. Okay, so now the other topic that is there, that is catalysis. So catalysis already I think you have studied in your school book. So this is little easier topic, catalysis. So what is catalyst? What is catalyst?
Sir, catalyst is basically something which is mixed in to change the rate of reaction. Generally, it is in positive sense to increase the rate of reaction.
Okay, so will it participate in the reaction?
No, sir. It will not
No, sir.
participate in reaction. Neither it will be consumed in the reaction. It will
And
only affect the rate of reaction.
and its state, chemical state or composition or amount will change after the
No, sir.
reaction?
No, sir.
No, sir.
Okay, that means it will be a compound, chemical compound that will not participate in the reaction, but either it will increase or decrease the rate, and after the reaction you will see its amount and composition remains same as it was before of the means before start of the reaction. Okay, so the general definition of catalyst you should read, because I think you have already come across the concept of catalysis. Why catalysis is required? Catalysts are required.
Sir, because some reaction are very slow in nature, so to
Hmm.
increase their speed, we need some chemical compound to increase the rate.
Okay, so how catalyst works? So I already shown the energy profile diagram for a normal chemical reaction. So if energy profile is like that, so this is your reactant and this is the product. Okay, so this is energy, y-axis is energy, and x-axis is reaction coordinate. So this is arbitrary. So reaction coordinate says that reaction will convert to product by passing through a transition state. Okay, so the energy difference between the reactant to transition state is known as
Activation energy.
activation energy. Okay, and the energy difference between reactant and product, that is known as product minus
Enthal
enthalpy, delta H. So in that case, enthalpy is positive or negative?
Sir, negative.
Negative, because product minus reactant you have to do. Always product minus reactant, final minus initial. So this is negative. So the profile is for exothermic reaction.
Exothermic.
Yes. So because product is energetically more stable than the reactant, so extra energy or it will dissipate as heat. Okay. So this is a profile for exothermic reaction, what I have drawn here. So if you want to draw endothermic, then the product energy will be above the reactant. Okay. So it will be endothermic. Delta H will be positive. So general profile I have shown for a common reaction. Now, if you add catalyst, what will happen? Catalyst
It
will not,
provides
it will, if I consider from the point of positive catalyst, then it will
provide
reduce.
an alternate path
Hmm,
for uh, to reach the product, which
yes.
is low in activation energy.
So main is thing is it will reduce the activation energy.
Activation.
Okay, but that means you can see from the figure that reactant and product that will be same. Only thing the height, that E activation, that is without catalyst. Without catalyst, WOC means without catalyst. So without catalyst it is higher as compared to with catalyst. So this is activation energy with catalyst. So react with catalyst you can see it is shorter. That means it has reduced the energy barrier. So that barrier is lower. So you can easily cross over from reactant to product. That means forward reaction is faster if you use the catalyst. If I consider the reversible, because all the reactions you can consider as reversible, that forward reaction as well as there will be some backward reaction from product to reactant. That's why we can write reactant to product, and then there will be a equilibrium constant that will be given by the ratio of product by reactant, and there will be a continuous reaction from reaction to reactant to product as well as from product to reactant, and you will have a equilibrium constant. If this equilibrium constant is very high, concentration of product by concentration of reactant, if the numerator is very large, that means product concentration is very large, we can say the forward reaction is almost dominant. Backward reaction is very negligible, means it is almost negligible. Then the concentration of reactant will be very less, but you can theoretically you can think that all the reactions are reversible. Reactant will go product and product will also go to the reactant. Now if I use catalyst, you can see the barrier height has reduced, that energy barrier has reduced, activation energy has gone down. So reactant to product, it will be faster. Now product to reactant, will it be faster as compared to without catalyst?
Sir, can you repeat the question?
My question is without and with. If you add catalyst, the backward reaction, now I am asking you to consider for both the cases. In one case without catalyst, another case with catalyst. Product to reactant. Now my question is, product to reactant formation with catalyst, will it be faster as compared to without catalyst? Product to reactant.
Sir, it depends which type of catalyst we are using. Like if it is negative
Negative
catalyst.
I'm talking about positive catalyst only. Okay. Just I have reduced the barrier, energy barrier, activation energy I have reduced.
Yes, sir, it will increase the rate.
Yes. So the forward rate as well as backward rate both will be increased. Okay. If you add catalyst, because you can see in previous case you have to cross the energy barrier if you want to convert product to reactant. When there was no catalyst, you see the height, how much it has to cross, very large backward reaction. Now when you have added catalyst, how much you have to cross? This much. That means you have reduced the energy barrier of backward reaction also. That means forward reaction is faster in presence of catalyst as well as backward reaction is also faster. That's why equilibrium will reach very fast if you add catalyst. Okay, so equilibrium means from forward reaction it is going fast as well as backward reaction also going fast. But what will happen if you add catalyst or if you don't add catalyst? The equilibrium constant capital K, that will remain same. Okay, so equilibrium constant is a ratio of product by reactant. Okay, so that will remain constant. You use catalyst or you don't use catalyst. Only thing, it will reduce the time. It will reach fast. If you add catalyst, the equilibrium will, you can achieve the equilibrium very fast by reduction of the activation energy. For forward reaction I'm talking about. Okay, so catalyst, forward positive catalyst, it will always reduce the barrier. So it can reduce by different means. So that is depends on mechanism, how it reduce the barrier. Okay. So you can generate some intermediate complex. You can create some weak bonding. So those mechanisms I can discuss when I'll talk about catalysis, how it works. But for positive catalyst, it will reduce. But for negative catalyst, rate will be slower. So first I will discuss about some positive catalyst. So positive catalyst means, so in language I should write. So positive catalyst means it will increase the rate. Positive catalyst increases rate by reducing activation energy. Okay. Negative catalyst it decreases the rate. Okay. So now the rate, how it can decrease, that will depend on some chemical reaction. Most of the cases some chemical reaction. So it is not like it will increase the activation energy. Okay. So the reduction of rate for negative catalyst, it is not like it is increasing the activation energy. Most of the time or maximum cases, positive catalyst will reduce the activation energy. That is always true. But negative catalyst doesn't increase the activation barrier. It generates some intermediate species or some chemical reaction will take place, so that it will not the reaction what is happening, that will be stopped. Just like if you have H2O2, H2O2 it will have a general tendency of decomposition into hydrogen and oxygen. So I can add here 2, 2, then 4. Now H2O2 decomposes into oxygen. So that reaction. If you want to stop, what I will add? I will add some amount of concentrated sulfuric acid. Here, concentrated sulfuric acid, it will make a weak complex formation with the hydrogen peroxide. That, as a result, it will not break down into water and oxygen. Okay, that does not mean that this reaction H2SO4 is increasing the activation energy. Okay, negative catalyst, most of the time it will give some weak complex or some reaction. It will with H2O2, in this case H2SO4 will do some reaction. As a result, its decomposition will be stopped. Okay, so negative catalyst works in different way, but our main focus will be on positive catalyst, because in industry or in laboratory our aim will be always to reduce the time. Okay, rate increases means time requires less, so that it can achieve the equilibrium very fast. That's why positive catalyst will have much more importance in industry. Negative catalyst also requires some time, because some chemical or some species that should not give the undesired reaction, that time we will add some negative catalyst. But most of the time we will be focusing on positive catalyst. Okay. So by saying so, you have to know different type of catalyst. What are the catalyst? You know, one is positive catalyst, negative catalyst. Positive catalyst, one common reaction. Always, I think you have studied in school book also. Haber process. That is the industrial process. In this case, what we will make? So that is the ammonia formation reaction, Haber process. So what catalyst you will use? Do you remember? Iron, okay, iron powder. So there will iron powder as catalyst, and you will use some other species like aluminum oxide, chromium oxide in addition to the iron. So what is this species aluminum oxide? What is its general name? Promoter. Okay. So it will increase the activity of catalyst. So iron will act as catalyst, and aluminum oxide or chromium oxide, some other oxide, transition metal oxide, they will give you, they will increase the activity of the catalyst. Okay, so that will be known as promoter. So how catalyst works? So catalyst normally we will use in, uh, there are two different type of catalyst. First I should say one is homogeneous catalyst or catalysis process is known as homogeneous. Another is heterogeneous catalysis or catalyst. Heterogeneous. So by word homogeneous catalyst or catalysis, so if I say the process is catalysis and the catalyst is homogeneous catalyst, another is heterogeneous catalysis. So what does it mean? Homogeneous means when the nature of catalyst or phase of catalyst same as reactant phase. So the phase means, solid, liquid, gas. If your reactant and the catalyst both are in same phase, then it is homogeneous catalysis. Okay, so a common example you can give, I can write next. I will write first, and the heterogeneous catalysis. In that case, catalysis or phase of catalyst different from reactant phase. Okay, so reactant and catalyst, they are in different phase. If reactants are solid, catalyst may be gaseous. So most of the time catalyst is solid, reactants are gaseous. Okay, so first I will give example of homogeneous catalysis. So for H2SO4 production, so first I will give example of homogeneous catalysis. So when reactant and catalyst both are in same phase, just like for H2SO4 production, the reaction is, that is SO3, so you can balance the reaction. Okay, so in that reaction, nitrogen dioxide act as nitric oxide, and this is nitric oxide, so nitric oxide act as catalyst. So here you can see sulfur dioxide, that is gas, oxygen, that is gas, and nitric oxide, that is also gas. So in this case, this is known as homogeneous catalysis, or the catalyst is known as homogeneous catalyst. Okay, And heterogeneous catalysis or catalyst, that Haber process I told. The phase is different. The example in Haber process, nitrogen and hydrogen. In that case, iron is acted as catalyst. So nitrogen is gaseous, hydrogen is gaseous, iron is solid. Okay, so this case it is heterogeneous catalyst. Okay. So these are like common examples you can remember. If question comes, give an example, you should write. These are the common examples that is industrially important. Okay. And now, other than positive and negative catalyst, there are several other examples, just like auto catalyst. Auto catalyst, have you heard before? Auto catalyst. What is auto catalyst? Auto catalyst. So auto catalyst is a, in that case, auto catalyst or catalysis, the process is known as catalysis. So in that case, one of the product will act as catalyst. We don't have to add any other catalyst from the outside. Okay, so one of the product that will act as catalyst, and it will increase the rate of the reaction. Okay, so that is one common example is oxalate. You have oxalic acid, you take, react with KMnO4, so it will oxidize the KMnO4. KMnO4 will oxidize the oxalate ion or oxalic acid, whatever you will take, into carbon dioxide. You will have manganese 2 plus, because KMnO4 oxidation state is +7, it will reduce to manganese 2 plus, and water you will have. Okay, now in that case, manganese 2 plus will act as auto catalyst. So this is one of the most common examples. So where a chemical species which which is the part of the product, when it forms, then it will catalyze the overall reaction. So initially reaction will be slow. Okay, this reaction will be slow, but once Mn2 plus has formed during the course of the reaction, that Mn2 plus will catalyze the reaction, and as a result, remaining amount of oxalate will be very fast oxidized into carbon dioxide. Okay, so this is one example of auto catalyst. So several other examples are there, you can see from the book, but this is a common example. And there will be, as I told, promoter is there. Similarly, promoter increases the activity of the catalyst. Similarly, negative sense, you have catalyst poison. Okay, so catalyst poison will, what it will do? It will reduce the activity of the catalyst, or catalyst will deactivated in presence of catalyst poison. Okay, so poison means, you know, catalyst poison, it will reduce or it will damage the activity or efficiency of the catalyst. So there are several type of catalyst, several type of poison. which will reduce the activity or efficiency of the catalyst. So you have seen so many reactions. Barium sulfate. Do you remember barium sulfate in your school book? Have you come across? Acted as poison. Hmm? Do you remember organic chemistry?
No, sir.
So hydrogenation reaction, have you seen with palladium hydrogen?
Yes, sir. It acts as poison in that
Yes.
reaction.
So normally barium sulfate we have to use little bit because we have to reduce some unsaturated double bond with hydrogen. Okay. You know hydrogen will reduce, and when we will be reducing with palladium will be the catalyst, and we will add a small amount of barium sulfate, linear catalyst. I think you have heard also. So that time palladium hydrogen, that is the palladium is your catalyst for the hydrogenation reaction. There we will add a small amount of barium sulfate also, so that it will control the reduction reaction. Okay, so if you add palladium hydrogen, it can reduce different type of double bonds. If it is carbonyl groups or C double bond C, C triple bond C. But if you add barium sulfate, then you can selectively reduce some specific chemical bond, not all. That means you will reduce the activity of palladium catalyst in presence of barium sulfate. So this is a well-known catalyst that is known as linear catalyst. Okay, so that is there barium sulfate acts as catalyst poison. And how catalyst works, there are two theory. Okay, so one is intermediate formation, another case it will form a adsorb species. Okay, so by I will complete by just show the general theories, how catalyst, positive catalyst normally, theories of catalysis. So one is intermediate theory. So intermediate species, intermediate formation theory or intermediate formation theory, compound formation theory. In it says that initially one of the reactant will react with catalyst and one intermediate species will form. So suppose one common reaction, as the few minutes back I was talking about, the formation of sulfur trioxide SO3. This is the reaction I just now a few minutes back I was discussing. Sulfur dioxide. This is important in industry because it gives you sulfuric acid formation in industry. SO3 when it will form, it will further react with water and it will give you sulfuric acid. Okay. So if I write the balanced equation, this is the reaction. So nitrogen dioxide and nitric oxide will act as catalyst. So in this case, first oxygen gas will react with nitric oxide. So step 1. So first I have written the overall reaction. Now nitric oxide, how it reacts, how it performs the catalysis. So first the catalyst will react with the oxygen and it will give an intermediate nitrogen dioxide. Okay, so this is the intermediate. And intermediate further in step 2 will react with sulfur dioxide gas and you will have SO3 and you will get back NO. So the catalyst, whatever NO was there, you are getting back in the second step, and in overall reaction you are having the so if I write the balance equation. So you can write 2SO2, I think it will match. Okay, so 4 to 6, balance equation, you just check once. 4 to 6, 6, and somewhere I have, so balance you can do it. If I just, this is a general reaction, SO3 4, so no need of balancing. So already balanced this is. So here NO is acting as intermediate, NO2 is the intermediate and NO is acting as catalyst. So this is, so this reaction supports the intermediate formation theory. And another reaction, which is another concept or another theory which is important, and that is used for heterogeneous catalysis, where one catalyst which will be different phase of the reactant. So most of the case, when you will use some metal as catalyst for the chemical reaction, so in that case, the second theory is adsorption theory. In case of adsorption theory, any question, it says on the metal surface, solid metal, you know that activity of catalyst will increase when we use the powder form, so that surface of the metal is increased. So if you take a metal piece and if you take same metal in powder form, activity of the catalyst will increase when you increase the surface area by making it a powder. Okay, that's why so many reactions, if you have studied, it is written turnings or powder instead of metal block. Same catalyst, its activity will increase when we increase the surface area by making powder or turning. Okay, so then what will happen? This metal, it will have large surface area, just like you can consider iron or nickel, whatever metal you are using. So so many reactions, nickel or hydrogen will be used for hydrogenation reaction. So hydrogen gas, initially it will come, and in the second step, on the surface of the metals, let's say this is a nickel metal, there will be some weak interaction with the hydrogen. So hydrogen, that bond will be now weaker due to the hydrogen will now interact with the metal surface. Okay, so you know hydrogen valence, it will have valency 1. So when hydrogen is making weak interaction with the metal surface, automatically the interaction between hydrogen among two atoms, it will be weaker. Okay, so the hydrogen bond now can easily dissociate, and if you have some alkene molecule, let's say ethylene, I am writing in a single step only. In the third step, first hydrogen will come and it will get weakly adsorbed, and then in the next step, alkene molecule which will reduced into the alkane, then this will start interacting with the hydrogen. As a result, what will happen? This bond will break, and then, so you can write, when carbon is making bond with the hydrogen, that means it will be not a full double bond, it will be a partial double bond, and then in the next step, the new bond between carbon and hydrogen will form, and okay, so you see, first it was ethylene, then it has converted into ethane, and this will be supported by the nickel surface. Okay, so by it will have weak adsorption. So adsorption is a process in which the chemical species, here hydrogen gas molecule, it will have weak interaction with the surface atoms. Adsorption means it is a surface phenomena where the weak interaction will take place at the surface, not bulk of the metal, because you have other nickel atom present. These are at the bulk means inside the below the surface. They will not participate. Okay, so what atoms will participate of nickel? Those are present on the surface. Okay, so adsorption is a surface phenomena where weak interaction, either through van der Waals interaction or through uh, weak chemical bond formation, will take place, and as a result hydrogen hydrogen bond strength will decrease, and in the next step when alkane will come and it will react with the hydrogen molecule, already its bond, hydrogen molecule's bond energy has gone down easily, it can react with the alkene to give you final reduced alkane. Okay, so this is known as adsorption theory. So adsorption theory we will use to explain the heterogeneous catalysis and homogeneous catalysis. You can explain through intermediate formation. Okay, so you can go through the PDF and you can study. So specific example of different type of catalysis, just like acid base catalyst as well as enzyme catalyst, I will discuss next class. So today I will stop here. If you have any question you can ask.
सर आई वांट टू आस्क वन थिंग सर, ये आप थर्ड मॉड्यूल के लिए मतलब क्या प्लान किए, क्विज या असाइनमेंट क्या मतलब?
तो आप लोगों का क्या प्लान है? मतलब टाइम तो शॉर्ट है, अभी एग्जाम भी आ जाएगा।
क्विज रहता तो ज्यादा सही रहता सर, क्योंकि केमिस्ट्री में ऑलरेडी 2 मॉड में असाइनमेंट मिल चुका है हम लोग को, फर्स्ट और फोर्थ मॉड में, और सर बाकी
ठीक
सब्जेक्ट में भी असाइनमेंट्स बहुत है, तो क्विज थर्ड मॉड में सही रहता।
ठीक है, तो बाकी लोगों का भी सेम ये है, मतलब
हाँ
ओपिनियन?
सर, हाँ सर, सबका सेम ही है। मेन सर एक बात ये भी है कि इस मॉड में सर न्यूमेरिकल क्वेश्चंस काफी पॉसिबल है, तो इस वजह से क्विज में थोड़ा सही रहता, सॉल्व करने मिलता।
ठीक है, तो you can go by the date first or second of, like it will come on Thursday, Friday, either first or second, any one
सर
of the
1 जुलाई।
July next
सर
month.
1 जुलाई will be I think appropriate, sir, because our chemistry lab has also finished, so sir Thursday it will be free for us also, so you can take in the evening.
Okay, so I
Sir,
can
from 1st
schedule
July
the
we
quiz.
will have our PPS quiz and workshop quiz.
So you decide the time, first, second, or Saturday, Sunday is third and fourth.
So we'll discuss and let you know about
No
the
sir,
schedule.
Saturday Sunday will be too late because we have our end sem from 5th.